Hello and welcome back to another episode of Math with Stone. Today we're going to be doing an AP question, and we have this guy on a bicycle. He's going to be going down a ramp, and then he's going to be jumping some cars, so he's a little Evel Knievel. All right? So it's only supposed to take 13 minutes. Let's see if we can do it in a little less time than that. So it's an energy question where we have the original height. We are allowed the angle right here. We're allowed the horizontal distance. We're allowed his mass if we need it. And it says derive an expression for the horizontal distance, x naught, in terms of all the other things and physical constants as appropriate. So one thing that's important is that we have gone down this amount, and then technically he got faster, but then we went back to here. So this potential energy turned into this diagonal kinetic energy. Diagonal kinetic energy, and that's an important detail to recognize. So if that is the case, then we would have mg h naught be turning into 1/2 mv squared. And those m's would cancel, and we would multiply by 2, and we get the square root of 2g h naught would equal the velocity that he would be leaving. I don't want to assume it's he. It could be a girl. That would be leaving this way, and how much kinetic energy as well for the most part. So with that in mind, now we want to know how far this person will go horizontally. So horizontally speaking, we are launching and landing from the exact same distance. So if we're launching and landing from the exact same distance, that means that the delta y essentially is 0 there. Okay? And we need to use kinematics. So if our delta y is 0, we would have delta y is equal to vi times t plus 1/2 at squared. That's one way to do it, where you would set this equal to 0, and then we would have vi for y plus 1/2 gravity t squared. But this way would be a little bit harder because we need to solve for time. And forgot my t there. There's an easier way that we could do it. If we figure out the time we get to the max height, then we would be able to figure out how far he would go. All right, so that would be a little bit easier. You could say v final for y is equal to v initial for y plus at. The time it would take him to reach his max height, the final velocity would be 0 at the top. We'd have v initial for y plus at, so it would be negative v initial divided by gravity would equal the time. So negative v initial divided by gravity would equal the time. And our delta x would be dependent on that time. Our delta x would equal its speed, vi for x, times that time, which would be negative v initial for y divided by g. Okay, so the issue that we have here is we have to find v initial for x and we have to find v initial for y, which are different, but we have this angle right here, which would also be that angle right there of the triangle. We know the speed that it left with, which I'm getting a little messy. The speed that it left with was square root of 2gh. So in order to find vi for y, it would equal square root of 2gh sine of theta. And this would be square root of 2gh cosine of theta because it's the adjacent. And then we would plug those in. So our delta x, or our x naught, is equal to square root of 2gh cosine theta times square root of 2gh sine theta. But it was negative, so make sure we put a negative there. And then we divide by g. Now these would end up canceling the square roots out, and you would end up with 2gh negative cosine theta sine theta all divided by g, h naught, x naught. Now there was an easier way, and it's not much easier. Instead of solving for time, what we could have done was we could have done v final y squared is equal to v initial y squared plus 2a delta x. Never mind, I was wrong. You can't do it that way. Ignore everything. This is the way. There might be a different way, but I'm not privy to thinking of it at the moment. So this is the answer that we got. Excellent. It only took 4 minutes and 45 seconds. It's supposed to take 13. We did better. Now, I do have an alternate problem, and this alternate problem is a little bit harder. Okay? So this alternate problem, it's saying derive an expression for the total distance that it would land if the bicyclist goes and lands on the ground instead. Now, this is a little bit harder because if he's landing on the ground instead, we still would have the square root of 2g h naught for the speed that he would leave with. But because we have this delta y that fell further, then it'd be a little bit harder. Okay? So because it fell a little bit further, the time in the air would not be as simple as negative v naught divided by g, blah, 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 blah. The time in the air would be a little bit more difficult to come by. Okay? So let's see if we can attack this one. It's going to be much harder. I apologize that it's going to be much harder. But here we go. So let's say that we have vi for y is still going to be the same because it's still going to be that square root of 2g h naught sine theta. Vi for x is still going to be 2g h naught cosine theta. All right. Now, delta y will equal vi for y times time plus 1/2 gt squared. That's one option that we could do. Or we could say v final for y squared is equal to v initial for y squared plus 2a delta y. All right. We know the initial. We don't know the final, but we could maybe find the final. Not easily, but we could try and find the final if we wanted to. And we do know the delta y is going to be h1, this height of the this part of the ramp right here, h1. Okay? But we could also get it this way. It would just be really, really gross because you would have to use the quadratic formula with an h1 in. So I think I'm going to use this even though it involves a little bit more complicated physics. I could solve this one and I could plug in my square root of 2g naught for this and I could plug it in and I could get a time, but it would be gross. So I'm going to attack it with this bottom formula and I'm going to also attack it with energy in this bottom formula because I know that when this lands, it's going to land with an actual speed. And I know that when it lands, it will also land with an actual speed for x that is going to be the same that it started with because we're going to ignore air resistance. So this is going to land with the square root of 2g h naught cosine theta. Okay? And that's this theta right here. That theta right there. This will land with a different angle. So that, I'm going to redraw. We got square root of 2gh cosine theta. This is going to be a different angle. I'm going to call it alpha. All right. This speed in which it lands would be determined by the total height that he lost, which would be mg h naught plus h1 would equal 1/2 mv squared. So it would be v would equal the square root of 2g h naught plus h1, which kind of makes sense. It's a little bit higher. It's going to have a velocity of a little bit more. So this is square root of 2g h naught plus h1. All right. Now we have two sides. We can find the angle. We could also do the Pythagorean theorem to find this missing side, which would be our v final for y. So I'm going to do the Pythagorean theorem. I don't think I need the angle, but I'm going to do the Pythagorean theorem with that. We got the square root of 2gh squared cosine squared theta squared plus, I'm almost out of room, v final for y squared would equal the square root of 2g h naught plus h1 quantity squared. All right. So this is going to cancel. We get 2gh cosine squared theta, which will have to be taken away from this. I'm running out of room, so I'm going to do a little bit in my head. We would have 2g h naught plus h1 minus that would equal the v final for y squared. And then we would square root it, and it would go here. But square rooting it is kind of silly because we could have just plugged it in to begin with. Okay. Thinking back, this is going to get us almost nowhere, will it? Oh, nope. No, it will. It'll get us somewhere. We're going to want the square rooting answer. I was realizing when we plug this in, we already have v final for y now. we have V initial for y, we have gravity, we have A, we have delta H, which would be H1. So this would tell us nothing, but there is another formula, V final for y equals V initial for y plus gravity times time. That one would be very useful because it's the time that we don't know. So V final for y, we just found out. It was the square root of all that hot mess. The 2g h naught plus h1 minus 2g cosine theta squared would equal, what is V initial for y? 2g, the square root of 2gh sine theta plus g times t. We could solve for time. We would subtract this, divide by g, and we would get time. After we get time, remember that our final answer for delta x would equal vi for x times time. So if that's the case, our vi for x is square root of 2g h naught cosine theta, and then we would multiply by time. The time, if we solve this equation for time, would be the square root of 2g h naught plus h1 in parentheses minus 2g cosine squared theta minus the square root of 2g h naught sine theta, all divided by g. That is what time is, and if we plug that in for time, we would get our answer with all the appropriate variables. Whew! Told you that one was harder. Unfortunately, there will be a problem similar to this, maybe not this level of difficulty, but similar to this on our test. So this is the advanced version of the one on the test, but the one that you will have on the test will be very similar to this or similar to the car problem. But honestly, it's similar to the alternate problem. It's a little bit more closer to the alternate problem. It's a blend between the two. I got another video coming up to teach you some graphs, but until then, stay positive, my friends. I will see y'all later. Bye.